Hello everybody, welcome back to another CIV E 398 assignment tutorial. In this assignment tutorial, we're going to be covering assignment 6, question 1. And as you guys will see, assignment 6 is all about the elasticity tensor. And what this tensor is it's basically a map that converts stresses to strains or from strains to stresses. So a common theme you guys will see in all these questions is you either get the stresses or you will get the strains. And you'll be asked to determine the opposite. So if I give you guys the stresses, chances are the question's going to ask you to find the strains. Or if I give you the strains, the question will ask you to find the stresses. So that's kind of the gist of this assignment. It's not too bad because the elasticity tensor, it looks really gross, but it's very easy when we're talking about isotropic materials, as you guys will see. So question 1 says the infinitesimal strain tensor is given as, and it gives us a nice 2x2 matrix. So we know if it's a 2x2 matrix, we're going to be given the components epsilon 1, 1, epsilon 2, 2, which are the 0.005 and the 0.02, as well as epsilon 1, 2. So that is the negative 0.002. And the question says if E, which is the Young's modulus, is equal to 20 GPa, and V is equal to 0.2, so that's the Poisson's ratio, determine A, the stress components sigma 1, 1, sigma 2, 2, sigma 1, 2, and sigma 3, 3 under the plane stress conditions. Part B says the stress components sigma 1, 1, sigma 2, 2, sigma 1, 2, and sigma 3, 3 under the plane strain conditions. C, the in-plane strain components epsilon 3, 3 under both plane stress and plane strain conditions. And finally, we wrap it up with part D, which says comment on the difference between the resulting stress components based on whether the plane stress or plane strain condition is assumed. So if we look at this question, the big thing that we're trying to find is going to be the stresses. And we're given the strain. So as I kind of alluded to, we're going to be given one thing and we're going to ask to find the other. But the one thing that we're going to quickly find out is we have a problem. If we look at parts A and B where we're trying to find those stress components, they want us to find sigma 3, 3. Now, if we look at the strain tensor we're given, we don't have epsilon 3, 3, we don't have epsilon 1, 3, and we don't have epsilon 2, 3. So how are we going to find sigma 3, 3 if we're giving none of the information about the strain? Well, the key to this question is understanding the plane stress and plane strain conditions, and that'll be what we're going to use to solve this question. So let's take another step further. So what do we know for a linear elastic isotropic material? Well, if we know the strains, we can find the stresses through the following equation. And as we can see, the elasticity tensor is very gross. It's a 6x6 matrix. It has a constant out in front. But if we really look at it, it's not too bad. And the reason why is because it only consists of two parameters, E and V, which were given. So if we look at this equation here, again, we're trying to find those stresses on the left. We have everything in this red box. It's not too bad. We just substitute it into Mathematica. However, do we know these strains? Well, from the question, we do know epsilon 1, 1. We know epsilon 2, 2. And we know epsilon 1, 2. However, as I said, we know nothing about epsilon 3, 3, epsilon 1, 3, or epsilon 2, 3. So the question is, well, what do we do? So again, we know epsilon 1, 1, 2, 2, and 1, 2. However, we're not explicitly given 1, 3, 2, 3, and 3, 3. So what do we do? Well, the first option that we have is can we assume that epsilon 1, 3 is equal to 2, 3, which is equal to 3, 3, which we just say is 0. You know, if we're not given them, they must be 0, right? Well, the answer to this is no. Please don't do that. You guys will get marks taken off because you guys will have the wrong answer. What we do have to do, or the proper way of doing this, is use the plane isotropic constitutive laws. And as I mentioned before, these laws are referred to as the plane stress and plane strain conditions. So we're going to look at both and we're going to try and determine, all right, how can these help us with our problem? So part A says use plane stress. So let's look at what plane stress is. The plane stress assumption is used when sigma 1, 3 is equal to sigma 2, 3, which is equal to sigma 3, 3, which is equal to 0. And the main takeaway here is sigma 3, 3 is going to be 0. And that's a key because if we look at part A of the question, it wants us to tell us what is sigma 3, 3. Well, if we're using plane stress, we know that sigma 3, 3 is just going to be 0. And what does this mean exactly? Well, this means if I'm looking at a material in 2 dimensions, this means that the in-plane direction, or into the page, if you will, that is allowed to expand and contract freely. And because of that, this allows us to simplify our elasticity tensor. So before we had 6 components in our vectors and then a 6 by 6 matrix. Now we're simplified down to 3 components in our vector and a 3 by 3 matrix. So if we look at this, it's the same thing we had before where if we're trying to solve for the stresses, we need 2 different things. The first is our new simplified elasticity tensor. And if we look, again, the only thing that's in this is going to be E and V, which we already know. Now, the problem that we had before was this strain vector because it had components that we didn't know, such as epsilon 3,3, epsilon 1,3, and epsilon 2,3. However, now it is simplified into simply epsilon 1,1, which we know, epsilon 2,2, which we know, and epsilon 1,2, which we know. So from this new elasticity tensor, we can solve for everything that we want because since we know the strains and we know the elasticity tensor, we can find sigma 1,1, sigma 2,2, and sigma 1,2. And then the question also asks for sigma 3,3, but if we look above, we know that under the plane stress conditions, sigma 3,3 will be 0. Now, part C of the question said, all right, that's great, you found all the stresses. But what about the strains in the in-plane direction? So what about the strain epsilon 3,3? Well, under this plane stress condition, it's actually very simple to calculate epsilon 3,3 using the following formula, where epsilon 3,3 is simply going to be the negative ratio, Poisson's ratio divided by the Young's modulus, and then multiplied by sigma 1,1 plus sigma 2,2. And where does sigma 1,1 and 2,2 come from? Well, they come from above. So the first step in this will be using the equation, or I guess the first equation, to solve for all of our sigmas. And then if we know our sigmas, we can find epsilon 3,3. Good to go. So that's going to be part A of this question. Part B says, okay, well, you guys did plane stress. How about plane strain? So as you see, there's a very bold, I guess, very significant similarity between these two. So the plane strain assumption is used when epsilon 1,3 is equal to epsilon 2,3, which is equal to epsilon 3,3, which is going to be 0. So the key here is epsilon 3,3 is going to be 0. And if we look back at plane stress, we use the exact same equation, but instead of epsilon, we had sigmas. So for plane strain, all these epsilons are equal to 0. For plane stress, all the sigmas there are going to be equal to 0. And this is used when, again, if we're looking at a 2D, let's say, plate, this means that the expansion or contraction into the page, into that third direction, is actually constricted. It's not allowed to expand into the page. And this allows us to simplify the elasticity tensor once again into the following form. So again, we're looking for those stresses. So we have the stresses on the left-hand side. And if we look at this, it's composed of 2 things just like before. The first one's going to be our new simplified elasticity tensor. And again, it's just a function of E and V. We can solve for that, no problem. And then on the very right-hand side, we have our strain vector, but now it's transformed in such a way that the only strain components that we need are the strain components that we already have. So epsilon 1,1, epsilon 2,2, and epsilon 1,2. So we're good to go. So from here, we can easily solve for the stresses. But then the question becomes, okay, well, I needed sigma 1,1, sigma 2,2, sigma 1,2. Well, that's no problem. I have my equation here. But it also asked for sigma 3,3. When we had plane stress, we knew that sigma 3,3 was equal to 0. No problem at all. But what about this condition? We know that epsilon 3,3 is equal to 0, but we don't know what sigma 3,3 is. Well, just like before, when sigma 3,3 was equal to 0, we were able to solve for epsilon 3,3. Now, when epsilon 3,3 is equal to 0, we can solve for sigma 3,3, which is going to be in that thickness direction, using the following formula, where sigma 3,3 is equal to the Poisson's ratio V multiplied by sigma 1,1 plus sigma 2,2, and sigma 1,1 and sigma 2,2 come directly from the formula above after we solve for it. So that's basically the essence of question number 2. We do part A and B using the plane stress and plane strain conditions, and then from that we'll also determine the strain into the page, so that epsilon 3,3, which is part C. And then what part D basically wants you to do is take your stress components that you found from part A and your stress components you found from part B and just compare them. So it should be a nice, easy question to get things going. It actually gets easier. Question 2 is much easier than this. So if you guys can do this one efficiently, the rest of the assignment will be a piece of cake for you guys. So that concludes question number 1. Thank you guys so much for listening. I will see you guys in question number 2.